Hello, a great welcome to Idea Statica tutorial. Myself Jarajan P. This is tutorial number 10. Here I will demonstrate how to model and perform verifications for a bracing connection. The example connection used in the tutorial is shown here. So let us start Idea Statica tutorial number 10. So we will start from a blank project. So as usual, we will write down the name as well as the descriptions. So let me write it as a pipe structure, and here let me write down the bracing BR1. We'll keep it for this project as 275. So let us take the S275 material. Okay, and let us go for M20. Okay, we'll increase it to M24. So let us choose it as M24.8. Okay, so we'll keep the concrete grade the same, and the design code will be as per EC3. So let us create the project. Now we shall start populating the various member components, the manufacturing operations as did in the earlier tutorials. So let us start populating the horizontal member first. So we shall add the member, the loads, and the operation using these menus. So we'll just add down member. We'll just add member, and here we'll be using basically the square hollow section or a rectangular hollow section as per the requirement. So we'll just press it. Okay, so we can use it as here we'll be using for the horizontal member as our K sections. So we can just take it as here we'll go to all, and we can go to the K section, and in the K we can select K to 120 by 120 by 8. So we can go here K, we shall go for K120. Yes, so this is K120 by 120 by it is a 8 we want. So this is the section. Okay, so this basically is a square hollow section. So H1 this is a horizontal member. Okay, this is a horizontal member. So as it is a horizontal member, what we do is for the EC identification, we can just rename it, and we will rather call it as, rather than M1, we'll call it as H1. Okay, so that is renamed to H1, and let us see the various parameters. This is a K120 by 120 by 8, and in the bracing it is important that we specify all the angles properly. Okay, so let us call this as a continuous member, and then we have all the beta angles. Here beta will be for this member, we'll keep it as 180. This will be my 180 angles, 180, and then we have the gamma, the pitch angle is a horizontal member, so it will be 0, and the orientation will keep the same, and all the offsets will be the same, and the rest of the parameters will be keeping the same. So let us start adding the other member. So we'll start adding the vertical member. So in the vertical member, okay, so for easy identification, let us just rename it. So rename, we'll rather call it as a vertical member, so it is a V1, so that we know which member stands for which configuration. And here we will, for the vertical member, we'll keep the same member size as the horizontal one, that is a K120 by 120 by 8, and this is rather it will be an ended member. And then we have, let us see, start populating the various angles. Beta will be obviously here, it will be 180 degrees, and then our gamma, and this gamma pitch angle, it is a vertical number, means that it should be 90 degrees, and the orientations will keep the same, that's a 0 degrees. And then this is basically what we do is that we'll keep this as a connection that will be designed only for the N, Vy and Vz. So this will be the force in the node. Let us keep it as a position as axis equal to 0. So we have populated the vertical member as well. So now let us go for modeling the various diagonal members. So as seen in the sketch, we have to model 4 diagonal members. So what we can do is that we can start again as usual, add the member. So let us rename it as D1. So rename, we'll call it as a D1 so that we know that it's a diagonal member. Okay, then so in this diagonal members we'll be going for the AC type. So let us start adding the members. So it is so this is AC, so we can call it as just add it all. So this is AC, and in AC we'll call it as a 120/80 by 6. AC 120 by 80 by 6. So this is 120/80 by 6. Okay, so that's all right. Okay, so diagonal member size is already modeled. Only thing is that we need to specify its angles now properly, and it's an entered member, and this is defined by the rotations. And for D1 we'll have beta is equal to 180 degrees, and the pitch, the angle which it makes with the vertical, it will be 30 degrees. So that is very important, because in the case of diagonal members the specification of the right angles, and in this case what we do is that we'll rotate the cross section 90 degrees so that we get the right orientation. So 90 degrees. So now let us just see this in the elevation so that I can tell you how to take care of the other parameters. So this is my plus y. So as you can see here, some kind of an offset is required so that this diagonal member can be properly spaced. And so as per our calculations, the diagonal offset EY is chosen as -20. So let us keep it as a -20 so that you will find that it is being properly spaced. Yes, as you can see that it is being properly spaced now. So, and the alignment node, all the loads will be at the position x is equal to 0. And so that's okay for the first diagonal. Now let us start populating. So all the diagonals are of the same size. Only thing is that we need to change some angles. So it is better that we just copy this diagonal. Okay, copy it, and let us first rename it so that it is a D2. Okay, so it is so we can rename it. It is as D2. So that's okay. And we'll have the same member size, that's an AC 120/80 by 6, and this is ended. And only the orientations in this case, obviously we have to go for beta is equal to 0 degrees, and our gamma will be here 30 degrees. Okay, so that is okay, that is given here, and alpha is equal to, and we'll change the rotations, that is just 90, and this will be minus 20. So as you can see that it is already been populated. Okay, so that's so we have it is for D2, our beta angle is 0, and our the pitch angle, it will be 30 degrees. It is the angle which it makes with the horizontal plane, and alpha is an angle that determines the orientation of the member. We have rotated by 90 degrees, so that's the reason why we have given alpha is equal to 90, and the offset we have conveniently fixed at -90, -20, and the load positions are recognized x is equal to 0. So that is the modeling for the member D2. So let us start modeling the other members as well. So we'll just call it as so just copy this, that will be better for us. So we can as usual we can just rename it and call it as say D3. So we'll call it as a D3. Okay, so the member dimensions will be the same. Only thing is that for here beta will be, we have to change it as 180 degrees because it is on the other side. It is 180 degrees, and the pitch angle here, it is the larger one, but it is on the downside, so it does mean that we have to we'll give it with a negative sign, so we'll -55, and the orientation will be kept as usual as 90 degrees here also, and all other parameters will be kept the same. Okay, so that is all regarding the definition of a D3. So you can see that how the member looks like now. So it is okay, so we have modeled 3 diagonals. The last diagonal is remaining. So as usual, we can just copy this D3 to another member so that the filling of these details will be the same. So Idea Statica helps us to generate the models at the earliest in a very convenient way, saving our valuable time. So let us just rename it. So we'll call it as a D4. So that's okay. So D4 is so we'll keep the size the same, and and only thing is that the beta here it is on the other side, so we'll again change this beta as 0 degrees, and here we'll keep it as a minus 55 the same, and this the orientation of the cross section is mentioned to the 90 degrees. Offset will be kept the same, okay, and the position of the loads etc will be the same at x is equal to 0. So as you can see that the model is generated. So now here it is important that we for here we find that M1 H1 this member is chosen as the bearing one. So here we can see instead what we'll do is that we will try to keep V1 as the bearing member. So what we do is that we'll keep V1 as a set bearing, process set bearing. So it does mean that from H1 we have changed it to V1. So as you can see the model basically consists of okay, so now it may look a little bit clumsy because we did not do any kind of manufacturing operations. So just I think it is better that we, so you can see that there is a horizontal member, all are actually rectangular or square hollow sections, and there's a horizontal member, there's a vertical member, and as you can see that there are four diagonals meeting at the joint. So it is important that we use the right kind of the manufacturing operations. So let us start updating this model and bring it to the final shape by applying various types of manufacturing operations. So let us proceed to add the cut manufacturing operation first, because as you can see that this member, H1, D1, V1 and D2, they have got they cut each other, and you need to see that all these members are being properly corrected using the section cut command, okay, of the manufacturing operation. So for example, if you see the, so we can say that here yes, the members, look here, the members go inside. So we need to make the proper manufacturing operation to clear all this, the common parts. So let us go straight away with the operations. What we can do is that we can straight away go for the cut. And here first of all let us start with say for example regarding the vertical member. Okay, so we'll have this is a cut one. Okay, we'll choose the member 1 as V1, and it is cut by this horizontal member H1. Okay, so both are the members, and all these things the bounding will keep it as a bounding box, closer, parallel, and offset as 0. And here basically we don't want any kind of a connection between the vertical member and the horizontal member. So what we do is that regarding the welds, we'll keep it as here no weld, and in the web boards we will assume that there are no weld. So here as you can see that we have to now clear other members. So V1 is properly corrected using the section command. So it is regarding the cut command applied on the V1 and H1. So now let us start just copying this so that we'll be able to enforce the other manufacturing operations very easily. So let us just copy it, and here we'll have the cut to, and in cut to what we do is that we'll choose instead of P1 we'll choose a diagonal member, that is our D1. Okay, D1 and our H1, D1 and H1, and all other parameters will keep the same. And at the same time we want that there is no connection, there is no welding connection between these D1 and H1, so we'll select just no weld. Okay, so that is regarding about the cut to. I will just copy the cut to again. Okay, so we can just copy it, so that will be cut 3, and in cut 3 what we can do is that we can choose the diagonal D2 instead of D1. So this will be my D2. So and that is D2 with H1 is the cut command, and all other parameters will remain the same. So now if you see, you can see that it is all through. Okay, that means the top members are being properly, if you see the inside you will find that all the top members are being properly cut. Okay, at the top side of the horizontal member H1 through this 3 cut operations command. So now let us having completed the 3 cut manufacturing operations, let us go for the modeling plate, so which is again performed through the manufacturing operations. So we'll have the manufacturing operation add, so we have to go for the stiffening plate. So let us see this is, yes, this is the stiffening plate. You can select it, and the stiffening plate is the SP1, and let us start provide all the necessary parameters. So for the stiffening plate SV1 we'll choose as 275, and the thickness will keep it as a 10 mm, and the size will be say rectangular, that is so I think that it is yes, this is the stiffening plate. Right now here we need to change the rotation angles. Let us just find out, or let us just change it and bring it to the recorded rotation. So by default this is the position of my stiffening plate. Okay, so what we can do is that we can make all the size specifications, and B1 will keep it as 275, so this will keep it as a 275, and B2 say the same 275, so it is a 275, and then we can keep our H1 as 190, so H1 we can keep it as 190, okay, and all these parameters, and H2 we can keep it as a 320. These are all pre-calculated dimensions so that we can house all the connections together in this simple stiffening plate 320. And here it is important that as you can see, this is now okay, it is created now in a horizontal plane. So it does mean that we need to rotate it. So this rotation will choose it as Rx. It has to be rotated about x-axis. Let us rotate it by say 90 degrees. So this is 90 degrees. So we have it as a 275, 190, 320. Okay, so I think that must be okay. So this is my, so sorry, I think that here we'll keep it as 0, and instead this R is the rotation angle that we have to change 90. Does mean that now yes, it has come to the, so as you can see that the manufacturing operations are in progress. This may not present a good view as such. Okay, anyway we can check that. Okay, or okay, the stiffening plate is properly created, so fine. So we need to carry out okay, many manufacturing operations on the stiffening plate as well. So that is all about SP1. So as you can see that as this is stiffening plate, it cuts through the various members like D1, V1, H1, all those things. Okay, it intersects all the members. Means that we need to perform the right kind of the manufacturing operations in order to see that all the components are being properly connected to this stiffening plate SP1. So now let us start performing the various cut operations regarding the stiffening plate. Okay, so what we'll do is that we'll again perform the operation, that is our cut operation. And here for example here we would like to have the horizontal member, so we'll choose member as my H1 horizontal member with, we want to find out with the cut by the plate, so we'll choose it as my SP1. Right now we have got only one plate, SP1, and we'll choose it as H1 and SP1, and this will be the surface, and this we'll choose it as the surface. And now regarding the welds, so regarding on the flanges we don't apply any welds. So what we'll do is that we don't apply any welds, and on the web what we do is that we will choose the weld of say 6 mm. We can straight away type it as 6 mm, and this is on the we can have it on one side. So it does mean that we have generated a proper connection H1 and SP1. So let us just quickly look what kind of a connection we have generated. Look here. So as you can see that, so look here, this yellow line, that's a weld operation. Let me just move it a little bit up. Yes. So what we have achieved through the cut for operation is very simple. How this SP1, that is the the stiffening plate, is connected with the horizontal member. That is, so as you can see, just to do a rotation here, simple rotation. So you can see that the welding, okay, the welding operation between the stiffening plate and the H1 is performed. So you can see that it is performed, this weld, okay. So it is performed on both sides. So it does mean that now this SP1, it is welded on both sides of H1, okay. Now so let us start performing other cut operations, okay, that makes us ensure proper connectivity between the stiffening plate and other components. So let us just start copying. Okay, so this is a web basics, so we'll just copy this, and that is my cut file. So here obviously I want to ensure the proper connectivity between okay, the stiffening plate and the diagonal D1. So what I will do is that I will select it as a D1 here. Okay, D1, and in this case what I will do is that I will choose okay, here it has the weld sizes. So what I will do is that here I will choose it as a, for example, here it is, okay, for the front size. So we can copy it as, if I take it as 0, so you may ask me why this is 0 is typed. So this just to show you, there is one more option. For example, here a 0 means that it is determined automatically by the program. Okay, so this is also one way of okay, ensuring the connection between the two parts. Okay, and please see that the right kind of the welding operation is also selected here. Okay, so as you can see this, so see this is how the diagonal is connected with SP1. So look here, so it is connected on both sides. So it is important that we okay visualize all the connectivity, okay, after a particular manufacturing operation is conducted. Okay, so that is being done. And okay, on the bottom also we have got some kind of a welding operation. So that is cut 5 is okay, done, performed for D1. Now let us perform it for the other D2 diagonal member. So we'll just copy this, copy. So that's a cut 6. So instead of what D1, what we need to do is that we have to select D2. So we'll keep the same thing. Okay, so it does mean that we have the D2 at SP1, and immediately check what kind of activity has taken place over the joint. If we find that this particular plate, okay, this stiffening plate, it is welded with, okay, welded with the, okay, the member D2. So what exactly is happening here is, okay, first the stiffening plate, okay, that will be welded with, you know, the slots provided in the member H1, and then what happens is that this member can be either brought to the side and then welded at side to the stiffening plate. So we have seen that the proper connectivity is already ensured. Now what is required is we have to have a connection between a, okay, this vertical member also that we have not done. So let us just copy this again, because as you can see that right now there is no connectivity, okay, between the stiffening plate and the vertical member. So what we do is that we just copy this again, copy. So we can say, can find we have got a lot of manufacturing operation here, cut 7, and that we will select with the V1, that's a vertical member. So you can see that, yes, so you can see that the model is also getting updated fast. Okay, and what we do is that here flanges will not provide any kind of a welding over here. Okay, so with the flanges and for with the web of the section, this is the web, means the web of the section we want to weld to the stiffening plate. Okay, so that we'll do it by using here a 6 mm. We'll specify here as a 6 mm. Okay, so as you can see, please check again the what kind of a operation was carried out. You can see that this section was properly, okay, so you can see that it is welded. Okay, the section, that's a vertical member V1, is properly welded with the stiffening plate. So it does mean that all this, you know, 1 2 3 4, that's a 4 5 6 and 7 manufacturing operations ensures that the stiffening plate SP1 that is properly connected with the diagonal members D1 and D2 as well as the vertical member V1. So let us go for the other manufacturing operation now in order to mobilize the connectivity for the bottom diagonals D3 and D4. Now the diagram members D3 and D4, it will be connected to this stiffening plate SP1 through a connecting plate. So in order to ensure that we need to add 2 more what we call as the manufacturing operations for the connecting plate. So let us start adding the connecting plate operation. So just add the operation. So the connecting plate. So okay, so we have the connecting plate. So let us go for the right kind of the boards. So we have 0.8 M24. So okay, okay, fine. So as you can see that a connecting plate is already generated, which we need to modify. Okay, so we want to see that is this CPL1 connecting plate 1, it is for the diagonal number D3 and D4. So first we'll generate the operation for D3. So we'll select it as here D3. So it is D3, and it is connected to a new plate. So it's not a new plate. We want that it is connected to an existing plate. It's an existing plate, so that you know that it's an existing plate, it is SP1. So the exposition, let us just input where the member has to be connected. So let us keep it as a 320 mm, 320 mm, and then we'll have it as 275, and let us keep the thickness as 15 mm instead of 10 mm. So we'll keep it as a 15 mm, and we'll keep it as the front. Okay, and we have got the type. We'll keep the type as not the cap plate. As you can see that here is shown a cap plate. So we'll keep it as a notch plate rectangle. Okay, so you can see that automatically the way in which the connecting plate is okay arranged with the stiffening plate is already changed. So now let us populate or the length and the width. So this is an important parameter, that's the type. So the plate length, let us have it as a 170 here. So this is 170, 170, and let's have the plate width. The plate width will keep it as a 160. So 160, and then we have got the overlap between the plate and the member. So let us keep it as a 150 mm. Remember that these are all being pre-calculated, so which is an important job in the connection. And the plate eccentricity, let us keep it as a 15 mm. Okay, so that. So here's the 15 mm. Okay, so it's fine. Now at the same time, we find that connecting plate is connected to the D3 to the welds. That is a tie weld we call it as, and the corresponding weld size we'll choose it as say it is a welded dimension. We'll keep it as a 6 mm. So this is let us keep it as a 8 mm here. 8 mm. Okay, so we have got all the welded dimensions. So 8 mm. Okay, and we'll keep it as on both sides. Okay, so we have the tongue weld properly done, and inside weld we'll keep it as 0. And regarding the bolts, there's a bolt configuration which is used to connect the connecting plate to the stiffening plate is to be properly defined. So it's at 24.8, and the reference line will keep it as member x-axis. And let us keep the rows, define the rows. So this is my 40 and this is 80, and let's keep their positions properly. So this is this should be, this has gone out, it doesn't, this is minus, it should be minus, okay, minus. So then yes, it is inside, so let us specify the positions as 50, and then we keep it as a 70. Okay, so as you can see, so we have populated for boards. So this is a grid. Okay, all these dimensions will be regular, and all other parameters remain the same. So we have properly created the so-called the connecting plate that connects the member. So the CP1 is a link between the diagonal number D3 and the stiffening plate SP1. So let us create a similar connecting plate for the diagonal number D4. So what we need to do is we need to just copy this manufacturing operation number to D4. Okay. So let's just copy this. So CPL2, we need to make only one modification in CPL2, that is it must be the member D4. Okay. So once that is the D4, you can see that it's being automatically done. Okay. So we have look here. So all the parameters are kept the same, and now this is the final model. So before going for applying the load effects, let us start modifying this SP1, that's our stiffening plate, so that we can introduce some additional chamfers here at these two corners. So you can straight away go for the editor, and the editor what we can do is we can add a small bevel, and we can say that here it is the dimensions are, we'll keep it as a 180 and 135. So this is 185 and 130. So 185 and 130, 130, 130. Okay, so this is 1. So you can see that yes, a bevel is created at 1. So let's just copy it to have it on the fourth side also. So we'll just copy it, and here we'll keep it as the fourth one. That's the selected column is the fourth one, and we'll just swap this 130 and 185, 130 and 185, 185, 185, and okay. So as you can see, okay, the bevel edges are made parallel to the bolt axis, approximately parallel. Okay, so we can just apply it, apply, and we can just okay it. So now you can see that okay, now the SP1 proper bevel edges are made, and you can see that this edge is approximately parallel to the bolt lines. Okay, now it's time that we start adding the load effects. So we can just put the load, and here it is important that okay, we start providing the various the load effects through the members. So let us start applying the loads. So here as it is, as we can see, h1 h1 you can see that it will apply it as a 300. Okay, so here we'll copy class as a 300. So what we can do is that before that we'll just ensure that we check equilibrium. Okay, equilibrium check option is applied here, so that what we can do is that all the loads are okay properly balanced, and what we can do is we can finally check for the unbalanced forces. So start applying the various loads. So here we'll write on this as 300. So these are the critical analysis results that is being imported into. So that is h1, that's 300, and this is a minus 300, minus 300. Okay, so as you can see that this member is directly under compression, and let us go for the vertical member. Here we have kept it as 191.5. So this is 191.5. Okay, and then we have got all the diagonals being the tension. We have just applied as the tension numbers. Okay, 300, 300, and then we have the 300 and 300. So just to see finally what would be the okay, is there any unbalanced forces? Look here. Here we have find that there are literally no unbalanced forces in the x, y, and z directions. Obviously, we have a small moment of 1.2 kilonewton meter. Okay, that's unbalanced moment. So now I think it's a time that we start running the calculate the button, so that we'll come to know the various bolt forces as well as which are the critical components for this bolt connection. So let us just calculate it. So as you can see that the connection is done for the analysis is done for 100% of the loads, and the strain in the plates is slightly higher, 1.6%, and the bolts utility ratios are around 68%, and the welds are fully utilized. So in order to check the components, you just press the check, and we can get a distribution of the plastic strains, and also we can get a distribution of the total stresses. So press the plastic strain, and you can also just mesh it, so that we'll come to know what are the components. So look here, so we'll find that so the various regions where the plastic strains are accumulated, that is just the connectivity. Okay, where this okay, this particular plate, it is connected to the stiffening plate. Okay, at these locations, and if we see for example the other, see the what are the other locations. So look here, you will find that there is some concentration of the strains near the diagonal members connection. So these are all on the member itself. So and here it is on the plate, that is what we call as a connecting plate. So this is so you can see that here also you can see that on this member, so the stresses are concentrated, the strains are concentrated in this region, and you will also find that some kind of a utilization, overutilization in the weld. The welds are already 98.5, that is located over here. If we want, we can increase the weld size. So now that's all about the plastic strain. If we go for the equivalent stresses, yes, it is the equivalent stress distribution, and as expected from the strains, we find that the critical positions are nothing but the connecting plates as well as the positions of the stiffening plate, or what we call as the SP, okay, near the near the areas of the bolts. So also you can see that the diagonal members are also okay critically stressed near the connection points. So that's all about, and if you want you can also generate a report and see, and please subscribe to the channel so that you will start getting the notifications as and when new tutorials are uploaded. So thanks a lot and have a nice day, and also a very happy new year 2022.